Yeah, welcome from my side. Andrea already introduced me. My name is Michael Felderer. I have been involved in this community for a long time. Back then, professor at the University of Innsbruck, where I also organized PROFES in 2017. And therefore, I in particular want to thank Regine, Andrea, Valentina, and Andreas, because I know how much passion and effort it takes to make such a conference happen. And beginning of this year, I changed my role. I'm now director of the Institute of Software Technology within German Aerospace Center, which is somehow a German NASA. And I have a full professorship at the University of Cologne. And today I want to talk about a topic that is not so much in the focus of this community and has also not so much been in the focus of my work, but is becoming more important in society and also in business in general. And this is what I want to present today. I want to shed light on research software. Yeah? So in the context of German Aerospace Center, lots of software and other fancy things are around. I think this is what you will naturally associate with German Aerospace Center. Satellites, for instance, this was a mission where highly sensitive sensors for detecting low energy wood fires on Earth were tested, was launched. Then another space-related activity are, for instance, robots. In this case, Justin, that's a robot that is already used for training Mars missions. Yeah, it's a robot that brings rocks from the rover to the lander. For sure, also very much equipped with research software. And the third space-related activity that I want to show you are for sure launches, right? So DLR regularly does launches. This was one that was done recently. It was a research mission where both Einstein condensate, yeah, that's a specific state, physical state, its creation was tested under microgravity, and therefore the rocket with specific equipment was sent to space and also for sure driven by software. And this rocket was launched on December 2nd this year from Kiruna in north of Sweden. Yeah, there is a space center, and this is heavily used for European research missions. Yeah, so somehow a Cape Canaveral in Europe, if you want to call it like this. Yeah, but TLR is not only about space. Yeah, there are also other topics. The most closely related to space, aeronautics, is also part, and here we see something that links space somehow and aeronautics. Yeah, it was the SOFIA project, standing for Stratospheric Observatory for Infrared Astronomy, which is somehow a specific observatory to investigate the atmosphere of Venus from the stratosphere. But Aerospace Center is also about other topics. I mean, also about energy. Yeah, and here you see a recent project where, classical drones, not specific ones, were equipped with software to maintain and operate photovoltaic and solar plants. Yeah, and this is done fully automatically. And in general, these unmanned aerial vehicles are a big growing market in the aeronautics domain. Another big part is energy in general, energy research. Here you see a project that DLR did together with Spain. So this is a hybrid train running with hydrogen and diesel, that is now operated in the Pyrenees, at least in a prototypic mode, because German Aerospace Center is always about research prototypes, not about fully fledged industrial solutions. Yeah, and for sure there's also lots of simulation around. Here you see an example from the mobility research, yeah, that's run in reality, that runs in a cave, and it should simulate, yeah, the urban environment of the future with its different types of mobility that are around there. Simulation is important, and another important topic is also security research. Yeah, that's the fifth part besides space, aeronautics, energy, transportation, security research, and this is somehow linked to it. It's about the safe operation of helicopters in offshore wind parks, right? You need to safely navigate the helicopter there, and in order to test that properly, yeah, the simulations are performed. Yeah, also linked to security is also Earth observation. Yeah, German Aerospace Center also runs an own Earth observation center close to Munich, and there, for instance, image analysis was done this year when the earthquake in Turkey and Syria took place, and here we can see how the different tectonic plates move against each other. Yeah, and the most recent topic that I will then also come back later to in my talk is quantum computing. So German Aerospace Center is in general well known for running infrastructures, yeah, and at the moment a new infrastructure for quantum computing is set up, so with real quantum computers, mainly based on ion traps, and this is a prototype of this. Yeah, and for sure also that needs lots of research software around it to make that happen. But anyway, I will come back to that later in my talk. Let me introduce DLR also as an organization to you. It's a large organization and it's federal. Yeah, it's distributed all over Germany. It has overall about 10,000 employees. It is structured into 55 institutes and facilities, spread over 35 locations and offices, mainly in Germany, but there is also a Tokyo, Washington, Brussels, Paris office in DLR. And one institute within this 50, first I want to also highlight that 20% of these 10,000 people develop software. Yeah? It's not the typical business software development with large teams, yeah? But 20% of the people develop different types of software, may it be simulators, may it be machine learning models, may it be embedded software running on rockets, right? And satellites. So that's there, and this is really a large number, yeah. And if you would consider DLR as a software house, then it would be even in Germany one of the largest software houses. Yeah? And our institute, the Institute of Software Technology, is one of these 55 institutes, and it's in particular dedicated to software technology and to software engineering research in context of DLR domains. We have 200 employees, yeah, in 3 departments and in 3 main locations, which you can see here. They are well located, yeah, in Brunswick, which is mainly the aeronautics center in Germany. Yeah, also historically, there was lots of aeronautics there. In Cologne, where also the administrative headquarters of DLR is located, and the German Space Agency. And in the south, yeah, in Oberpfaffenhofen, close to Munich, where the space research is located, and also for missions, the Space Control Center. So somehow this is the German Houston, yeah, if you want to call it like that. Okay, that's us at our last institute seminar, and what our main topics are: software and systems engineering, mainly in the context of aeronautics, space, energy, transport, and security, yeah, with a focus on aeronautics and space software. We also do visualization, artificial intelligence, quantum software technology, and also high-performance computing, which is also closely related to quantum computing, as we will see later in my talk. But now you have seen that examples where software plays an important role in the research context. And my talk focuses now on research software. What is it? It's software that is created during the research process or for a research purpose, right? That makes it a bit different from classical industrial software, and I will come to that. And this software comes in different flavors, and this can be simulation software, embedded software, and a few other things, as I will show you in a few minutes. Research software is a central element of digitalization in academic and also industrial research, right? So today, lots of research is about developing research software, right? So it's a critical artifact for the entire research system. And I now want to guide you a bit through the different types of research software that we identified. So the first type, I think this is the type that you will all have in mind when it comes to research software, is software for modeling, simulation, and data analytics, right? So here you can see one example from our institute about structural analysis of airplanes. Another one, which is simulation, that was started during the COVID crisis. These are simulation models for the spread of viruses, right? And that was also done together with Robert Koch Institute and players like that. That's also a type of research software. And the third one, data analytics, is a software for space debris. That's a very important problem and topic in space. There were many missions in the past, and they all left some pieces in space, right? And we built a database with these particles, and compute their different orbits, and that information is then used for other missions to take care to avoid potential clashes. Okay, but besides this classical modeling, simulation, data analytics software, there are also other types of research software, in particular embedded control software that also plays a role for our research missions, right? So when the experiments in space are done, then you need the control software to make that happen. Then, third category of software are, I call it software prototypes in engineering research, which has a bit of different angle. The main angle here is really to have a software that might later be turned into a product, and that also shows a concept in engineering research. So here is an example of a 3D visualization of software with a island metaphor, but it tries to make the modules of the software visible in a 3D virtual environment. Another example is the virtual satellite software that is used to support the planning of the construction of satellites, right? So it supports the system engineering of satellites. And the third one could be a dashboard for security, right? Developed in research, where you analyze vulnerability information. And the fourth category of research software that we identified is infrastructure and platform software. That's software where other software might run on, right? Here you see a software called RCE. That's a software that we use to run computational workflows, right? So it integrates different computation tools, right? And runs them in order to perform simulations and visualizations. Yeah, and we do research, we develop software, but we also do empirical studies. Yeah, and here you can see one that was done by my colleagues already back in 2018, and it's about the software development in German Aerospace Center. And here you can just see what the programming languages are, the distribution of programming languages used in German Aerospace Center, at least back then in 2018. It was Python, which was mostly used, C++, MATLAB, and C. So this was the top 4. In the meanwhile, also Julia is becoming, for instance, very prominent. And yeah, that's about this. Yeah, but research software is not only important in the academic context. As I said, it's also in industrial research, it plays an important role, and it can for sure also become successful outside research. So here you can see examples. R is an example, Stanford NLP, NumPy, or scikit-learn. So these are all still research-driven software packages and tools. So now let me come to the point, what is research software and what makes it different from a classical software? Yeah? So the first thing is its goal, right? So the main goal of research software is to enable and support scientific investigation with the aim to create and validate knowledge. Yeah? Whereas business software normally has the goal helping to perform business functions with the aim to support running a successful business. Yeah? So that's the typical focus of business software. Also, with respect to functional requirements, research software is typically different from business software because in research software, the functional requirements are per default unknown, right? Because the way is the goal, right? You do the research, so you don't know the requirements up front, so you have to define them on the way in this typical research process of developing hypotheses, validating them, refining things, right? So you cannot define the requirements up front. And if you think a bit about this in more detail, then you find out there is a relationship between research software and maybe also AI engineering, where you have a similar setup here. But I will also come to that a bit later in my talk. And for sure, this also has then a consequence for verification and validation, which is per default difficult if your requirements are unknown, right? Because if the requirements are unknown, then it's much harder to define and prove whether a software works properly. And another big difference are also non-functional requirements. So in research software, typically not the ISO 25010 requirements are the key non-functional requirements, but the main aspect is reproducibility, right? So research needs to be reproducible in order to be serious research, right? And this is then closely linked to the so-called FAIR criteria that some people of you might already have heard, maybe even in the context of data, right? So research software needs to be findable by humans, by machines. It needs to be accessible. It needs to be interoperable with other software, and it needs to be reusable. This means and usable and reusable. Yeah? So someone else has to be able to also execute it, yeah, in order to reproduce it. That's an aspect here. So with respect to non-functional requirements, these FAIR criteria are the key non-functional criteria that matter in the research context. Yeah, and I mean, research context has been around for decades, yeah, but it has not been recognized a long time. Now the situation changes. Even in Germany, there is now a call, a DFG call, about research software, right, to investigate it with software engineering methods, yeah. And how did this stronger recognition in society came up. Yeah? So to some point there was the so-called productivity and credibility crisis in research software, and I want to explain this based on the so-called climate gate affair. What was that? It was back in 2009. Hackers leaked the email communication of climate researchers, right? And what they intended was to show that climate change doesn't take, has been invented, it doesn't take place, because of the communication that the climate researchers had in their email. Actually, this was just a misinterpretation of this email conversation. Actually, the climate models worked and the data was not faked in the climate models, so that didn't come out. But another result came out of this, and this was that the climate researchers were absolutely not able to handle their software, right? So they had absolute problems to maintain it. So this is the productivity crisis, and also, it decreased the credibility of research, because this email communication suggested that the models are even wrong because the researchers are not able to handle their software. And this is really a key experience that has been made because this software is really the basis for political decisions that infect all of us, right? Affect all of us, and in some cases infect if we come to Corona or so. Okay, so from this we can conclude that research software is a critical artifact, that is the basis for many key decisions in society and technology, and research software requires software engineering. That's the message that I want to place here. Well, so the first point that you can then say, well, I mean, there is the SWE book out there, right? The software engineering body of knowledge. Just download it, take it, and apply it, and your research software will work, right? But things are not that easy, right? And the reason for that stems back a long time. Does anyone know where this is? Where this picture stems from? I have expected that Dietmar knows. Yeah? Yeah, exactly. That's this first software engineering conference taking place in 1968 in Garmisch-Partenkirchen, funded by the NATO, not so far away from here, 2 hours about if you are driving fast. And this was the conference where the term and the discipline of software engineering was founded. And the thing was, this software engineering community, back then, I mean, it was funded by the NATO, it purely focused on mission-critical business and embedded software, right? I mean, to some extent, we also do this space-related mission-critical software. It was about processes, about generality, but one community was completely kept out, or even didn't want to be involved, I don't know. This was the community of computational science that was also around there already. This was the software that processed data and did parallel processing, right? They were not considered and involved in this process, and this has led from the beginning to the situation that this computational science community that also developed software was, let's say, completely separated from the software engineering community that focused on processes. We will see that situation changes a bit. And what is software engineering classically about? It's about resolving trade-offs yeah, between the functionality that you need to implement, the quality that you want to achieve or need to achieve, the time that you have, and the resources in terms of money, personnel that you have. Yeah? It's always about figuring out and dealing with these trade-offs in the one or other way. Yeah, and research software engineering is now the use of software engineering practices in research applications, right? I think that's a straightforward definition. But immediately the question arises, can we just take SWE-book, or is it a bit different, or do we have to adapt things, right? Here I have this symbol, RSE, because there is even a community around which is called Research Software Engineering, RSE, which is an international community of people that in particular want to bring software engineering forward in the research context, but also make policy makers more aware that this also needs funding. Yeah? So there seems to be some indication that it's to some extent different. Yeah? And I want to highlight a few points where it is really different. So the first difference is that research software is rarely developed by classical software engineers, yeah, but more by domain researchers. And this is, by the way, not only the case in academic research software, but also in industrial research software. So also if you look into automotive and other domains, right, the research software is typically developed there by domain researchers or engineers. A second big difference is also the time scale. On the one hand, research software is often very long-lived, and it's developed by teams that do it on the side besides their other research they do. Yeah? And this software might exist for 20, 30 years, yeah, until a professor retires or whatever, to say one example. And another big point is also that it's often developed by individuals that have time-limited contracts, right? So typically periods of 3 to 5 years, yeah, of a classical PhD. That's also a big difference. I mean, one could say in modern world, software developers also change companies very quickly, so it might merge a bit, but in principle, how the things evolved, it's a difference, right? And a third difference is also that overly structured software processes restrict research. At least from a historical perspective, this is a core difference because back then in the 90s, yeah, software development was always very heavyweight, right? And you had strict processes, document-oriented and so on, waterfall-driven, and this doesn't work for software at all, right? Now things change a bit, yeah. Also, software development is more agile, but in principle, when it comes to research software, then specific processes needs to be adapted, right? And this might not be the processes that work for business software. So let me come to these trade-offs of research, of software engineering, and instantiate them for research software. So with respect to functionality, yeah, the differences are that requirements are typically unknown in research software, and they are research related. This means, I will then show an example, it's often quite hard to understand them if you do not have the domain science background, right? Then quality criteria are different. I mean, mainly the FAIR criteria, yeah, findable, accessible, interoperable, reusable. That is what counts, and also verification is difficult per default. When it comes to timing, there are differences. There is this time-limited contracts that are all around in academia, and the processes are also restricted. And with respect to resources, so the point is often that the funding for research software engineering is limited. So it's not typically not a core business, but a side business, if you want to define it like this. Also, people now realize that this might not be the case in all settings. And the second point is also that the software engineering knowledge is limited, right? So domain scientists often, or engineers, mathematicians, physicists, they often have limited knowledge about software engineering. Also, they often think they know a lot, physicists or mathematicians, but when it comes to software engineering, in practice, their skills are limited if they do not learn them on the job, for sure. Yeah, but does it now mean we cannot use software engineering research results at all for research software engineering, or is it somehow in the middle? Yeah, for sure I would say it's somehow in the middle. Yeah, there is a overlap between classical software engineering research and research software engineering, and both worlds can also benefit from each other. And this is the key message that I want to motivate now in the second part of my talk, that these communities can really benefit from each other, and that there are exchanges in both directions, and that even the intersection is quite promising. So let me first start with what software engineering research can provide to applications, in particular in the research context. There is work out on this. I mean, there is a book that was edited by even a member of this community, Jeff Carver. Many people might know him. He has edited a book on software engineering for science in 2016. And from that book, I took 2 chapters to show examples where cutting-edge software engineering techniques can be applied to research software. One example is metamorphic testing. Yeah, I will show in a second what that is. And another one are domain-specific languages, which are in particular useful. So these are the screenshots that I took from the book. Yeah. Now, metamorphic testing. What is it about? First, it's about testing functions, right? And here we have a function for something which is hard to understand if you are not in chemistry or micro or bioinformatics or whatever. It's a function that computes the so-called duration radius of a molecule, right? Which describes the distribution of atoms of a molecule around its axis, right? And the formula, how this can be computed, you see here on the right. Yeah, you can easily see this I and J and the difference. So it can be calculated by 2 loops. Yeah, and then somehow you have the difference between the coordinates, and then you do the square root and so on, right? I don't want to go into math here, yeah? And at least each of us, even it took me some time to understand it, right? To understand this formula and to understand how it links to codes, right? So it needs some, at least willingness to dive into domains that you might not be familiar with if you want to investigate this with a pure software engineering background, right? So, but this might have been written, this code might have been written by a chemistry PhD student or a chemistry researcher in a research institution, yeah? And when this method should be tested, then this metamorphic testing is a useful approach, right? It's often hard to exactly say what the output is. So different from if you want to do a JUnit test for a function that adds 2 values, yeah, then you know if you want to add 1 and 2, then the expected result is 3, right? And if it's not 3, then your add function is implemented wrongly, right? And for research functions like this one, it's much harder to say this is the output that I expect. But what you can often do, and this is the idea of metamorphic testing, you can say if I transform my input value somehow, yeah, then the original result and the new result relate to each other in a specific way. And this is exactly done here. You calculate this duration radius with some arbitrary value, yeah, and you store this result here. This is the initial output, yeah, and then just from the property of this function, you see that if you permutate the values, then the result stays the same, right? And this is exactly what is done here. You permutate the values, yeah, and then you also store these values, and the assertion is then that the initial output and the follow-up output are the same given some epsilon, which might be the numerical difference just from the numerical perspective. Yeah? So this is what metamorphic testing is about. Yeah? If you don't know the exact output value, then you can at least relate output values under one condition with the output values under a mutated or transformed condition, yeah, and compare them and find out whether your test is successful or not. So that's, for instance, one testing approach that is very useful in the context of scientific software that has been developed by Chen and others in software engineering and successfully applied in research software. Another example where knowledge from software engineering, in this case model-based software engineering, is useful for research software are domain-specific languages. What you see here, I mean, I took it from the book. There are many other examples. What you see here is the classical stack, how numerical models are developed. Yeah? This is a model for marine ecosystems. So, for instance, to predict how the biomass of specific fish groups develop based on the temperature of the sea, of the air, and so on, right? You can take many parameters into account here, right? I'm anyway not a domain expert here, so I cannot tell you more about these models than what I just said. But the principle is often the same. At the bottom, you have a mathematician, data scientist, who knows about the mathematical and computational background of these models. Typical models are difference equations or differential equations or agent-based models. These are the classical types how simulation models look like on the level of numerical mathematics. And then on top of them, you might have different domain scientists that bring in their information. Yeah? Here it's an ecological modeler who knows the ecological models, then a stock modeler who knows about how many fishes are here and there. He knows about the biomasses and so on. Yeah, and on top there might be a classical software engineer doing the deployment of these models. Yeah, and it helps a lot if you abstract the different layers with domain-specific languages, yeah, and even generate code from these abstractions, yeah, as it has been done in classical model-based software engineering, developed primarily and originally in the systems engineering context. And here you see an example of such a domain-specific language. Yeah, you see in Eclipse environment. This is exactly this model that the stock modeler develops. Yeah, you can see here it's done for the Baltic Sea. You have defined time steps for the model. You define how much swimming speed specific species like herrings have and things like this. Yeah, and this is then the input to the model and used then to calculate this ecological models. For sure, there are many other relevant topics, and recently there was an interesting study that investigated people that did a PhD in physics and mathematics and then became consultants. Yeah, what they missed, what software engineering they missed in their physics and mathematics education that would have helped them for their research software during the PhD. And they in particular mentioned that agile software development and continuous software development is something that would have helped them a lot. So it's not only about the techniques, yeah, but also about training people properly. And this is exactly one thing that we do in German Aerospace Center. I mean, we have the possibilities for that. That's not always so easy in a university setting. We have a software engineering initiative that is, let's say, led by our institute, and it has four parts. Yeah? So the first one is community building and experience exchange. Yeah? So having a contact person in each institute responsible for software engineering practices in that institute, and having an overall software engineering responsible that is backed up with our software engineering research at our Institute for Software Technology. Then also guidelines and tools are needed. I will come to that in a second. And then for sure classical trainings. Yeah, new people, new researchers start on a daily basis and they need training in, for instance, so in agile and continuous software engineering to use that productively when developing their software. And finally also consulting, which goes a bit deeper. Yeah, there the group in our institute that runs this really works with that groups at other departments at DLR and helps them with testing and things like this, right? So this is some in-house consulting for research software development, if you want to call it like that. So just the 2 points that I want to highlight is this, first this how this community building works, right? It works in the way, I mean, this is also done in some companies when you might have some guilds or so, right? So these are the developers of other institutes. Yeah? We heard there are 55 in whole DLR, and most of them have a software engineering contact person, right? That is responsible for bringing the techniques into the software development of that institute. Yeah, and we at our institute we have the software engineering responsible for whole DLR, right? Who is also backed up with our research, yeah, and linked to cutting edge technologies and transforms that properly. And he's also related to DLR quality assurance and to the CIO of DLR. And besides that, there are also guidelines. I mean, it's becoming an important topic for us and in general also to think about how research software can be transformed and brought into and also be brought into industrial settings. And for that, guidelines are available to classify software, and there are 4 categories based on the decision criteria. So whether the software is distributed or not, yeah, and also whether it's there is a long-term development involved to that software, and the other third criteria whether the software is runs a high-risk facility, for instance, when it runs on a satellite or when it runs in an internal plant, right? Then it's a high critical software, so typically embedded software falls under this category. And depending on the category, also different guidelines for development have to be applied. Okay, now let me highlight one aspect where research software engineering can support software engineering research, yeah? Something that I would say is original from software engineering. And this is, for instance, when it comes to open science, right? Open science has become prominent in software engineering recently. There has been work on this by also colleagues that are known in this community, like Daniel Mendes or Stefan Wagner. And they promoted this open access, open data, and open source ideas, right? That this is needed to make research sustainable in software engineering. And they also highlighted that in software engineering, people are still struggling with that. And the research software engineering community tries even to go a bit further in this respect. It even tries to consider research software as an own citable artifact, right? Because, I mean, the relationship between publications and software might be an M-to-N relationship in general. And if you look into statistics of studies that were done, then you see that typically the software is not directly cited, right? This, but for instance, only in papers the software is mentioned in text name only. Sometimes with the its URL. Sometimes it's mentioned as an instrument. Yeah. Sometimes the project is cited that uses that. The software project is cited, or sometimes a publication where that tool is described is cited, right? And here people try to get further and develop the citation file format, yeah, that you can integrate in your CI pipeline of your research process, yeah? And this then even helps to deploy research software to Zenodo, right? And then you have a DOI for your research software and you can cite it directly. Yeah? So it tries to go here one step further to make the software directly citable. Okay, and now I have shown how aspects of classical software engineering help research software, how research software engineering specifics can impact software engineering research, and now I want to come to this intersection. Yeah? And there I see two interesting aspects that can be investigated. The first is software engineering and computational science that grow together, and the second one, even empirical research software engineering can be very interesting and have a fruitful interconnection with classical empirical software engineering. Okay, let's remind, yeah, in 1968, yeah, software engineering and computational science were separated, right? These were two separate worlds, yeah. And if you look into PROFES 23, yeah, then what we can see, there is a workshop and engineering process and practices for quantum computing, exactly a topic intersecting computational and software engineering. And also another workshop, computational intelligence and software engineering, again intersecting computational science and software engineering. So you can see PROFES 2023 tries to bring the worlds together that the NATO conference in '68 separated somehow, right? That's good to see that the worlds are coming together. And I want to show two examples where we can see that the worlds need each other. So the first topic is a topic that still a PhD student back in Innsbruck is working on. Yeah. It's about how to properly do online testing. So online testing means testing of machine learning models in context, so not isolated with just precision recall, but whether they work in an environment properly for collaborative AI systems. Yeah, and you see here this example. We have this robot arm, and the robot arm should not harm the human, right? The human hand and so on. And the human and the robot should together collaboratively put the bricks into the right boxes, and the robot should learn it via image recognition and learning algorithms, right? And you want to test that properly, yeah, and for that simulation is quite helpful. So we want to test this image recognition here, right? And we have a setup having a simulator in the middle, yeah, a simulator that can test this environment where the image recognition is embedded into such a setting. And we apply different search or optimization algorithms, yeah, where we try to get into a situation where we violate the safety zone, because this violation shows that either the image recognition doesn't work properly or that this is something that we need to test further in the real environment. Yeah? Because the image recognition might depend on the illumination, on the speed that the robot arm has relative to the human hand and so on, right? But also here, the domain concept do not matter. What I just want to highlight, in order that we can do that research, yeah, we need let's say at least a mid-fidelity simulator, right? And it took us back in Innsbruck lots of effort to come up with a non-trivial simulator implementation based on CobeliaSim and OpenCV to test our optimization algorithms, how well they operate, and to come up with our testing approach for this image recognition. Would we have collaborated with researchers that have such simulators already? Yeah, this would help us a lot. And on the other hand, software engineering is very good in coming up with process models, like for continuous development of machine learning models. And that for sure also helps research software engineers when maturing their machine learning models, right? So to sum this up, in AI engineering, right, when engineering AI solutions, the two worlds, the research-driven and the software engineering-driven world, can benefit a lot from each other. So the computational science world can offer fair, yeah, not fair in sense of findable, accessible, interoperable, reusable simulations, mathematical models, and heterogeneous large-scale data, and even nice use cases, right? I mean, you have seen the DLR use cases at the beginning for AI engineering settings, right? Even settings that are so fancy and new that business doesn't have them, right? So that's, I see a big asset that the computational science world can provide. On the other hand, software engineering can, for instance, provide software engineering processes and techniques, yeah, that can be adapted to a specific AI setting. The second area where I see this close link is quantum computing. Yeah? So quantum computing is a multidisciplinary field that has aspects of computer science, physics, mathematics, that utilizes quantum mechanics, yeah, to solve complex problems in the mid-range faster than a classical computer. That's the idea behind quantum computing. And there are several problems that can prospectively be solved by it. Here is what we think is the scale when a specific problem can benefit from quantum computing. The first problems that can benefit are actually quantum simulation, meaning you want to simulate quantum effects in molecules or atoms, yeah, with a quantum computer. Yeah? That's some kind of analog computing that's the most realistic application case in short term. Then combinatorial optimization, a next problem that benefits then on a longer range. Also quantum enhanced machine learning might become feasible, and finally even classical simulation of with differential equations and so on might benefit. Yeah, so that's the let's say the problems that might benefit from quantum computing, where we stand now in the order of time based on the error correction that is needed. But also here, I don't want to dive into the details. I just want to highlight where in particular also we are working on and where we see links. So first, for quantum computing, you need a quantum computing software stack. What does this mean? At the bottom, you have different realizations of quantum computers, may it be on iron traps or on superconducting qubits and so on, right? That's physics. And on the top, you have your application problem. May it be this quantum simulation, may it be an combinatorial optimization problem, machine learning problem, whatever, right? Then you have algorithms that tell you based, for instance, on quantum circuits, how to solve the problem. And then you need a compiler, that compiles your algorithm into some code that can be executed on a quantum computer, right? And this compilation process is specific, and this needs a quantum hardware and software co-design. And here, techniques from computer science, programming languages, and also software engineering help. And where software engineering even helps more in the context of quantum computing, according to my opinion, is when it comes to quantum computing platforms. So quantum computing platforms are broader, right? There you do not consider the quantum computing in isolation with its compiler, but you consider what will be needed in order to solve real broader problems. You will need hybrid computing, combining quantum computing with classical high-performance computing, cloud computing, and things like that, right? And here you will need an entire platform. You need also techniques, for instance, from real-time engineering, also from DevOps, to make that work properly. And these are software engineering topics that will be required to bring this computational science, this research-driven computational science problem to the street and into the concrete applications. So to conclude this, the recent disruptive technology of quantum computing relies on physics and computational science, and is based on research software like this one. And software engineering is required to develop the quantum software stack and also to provide quantum computing platforms. So it's great to have these two workshops that took place yesterday here at PROFES. So we have now seen that software engineering and computational science is in this intersection where the both worlds can benefit from each other. And there is another area that I want to finally highlight, namely empirical research software engineering. What does this mean? This means that research software provides many interesting application contexts that even empirical software engineering can benefit from, right? Let me give you examples. So in research software development, you always have to deal with development under resource constraints, right? So you have limited resources, and that can be an interesting investigation context that might be similar to what you observe in startups, for instance, right? Then you have to deal with highly dynamic requirements and complex domains, right? Which might be linked to data engineering settings or AI engineering settings. You have to deal with long-lived software artifacts and reuse of them, which might be a very interesting observation context if you want to investigate technical debt or maintenance of software, right? Or product line engineering, things like that. And this is the next thing. You want to deal with fast configuration spaces. That might be very promising for product line engineering approaches. And finally, you deal with software development that is mainly done by domain experts, which might be a very interesting application case for low or no code applications. So research context provides interesting application cases for empirical investigations. And finally, there is also little knowledge about the relationship between traditional software engineering and research software engineering that might be worth investigating. Yeah? So to provide examples, what are suitable business models for research software? Could be such a question. Another one, how to organize software-centric scientific processes. Another one, what is specific about research software engineering compared to other software engineering specializations? Then, which skills and educational formats are required for research engineering practitioners? What are the types and maturity levels of research software? How to integrate software engineering techniques into research software development? And finally, is research software of poorer quality than industry software? Yeah, we do not really know, I would say. Yeah, that's it. And same as Regine, I for sure also want to make the announcement that we are hiring. So for instance, we have one offering on developing testing approaches for quantum software. That's one example, or how to do generative AI in the context of research software development. Yeah, so if you are looking for a PhD or postdoc job, then don't hesitate to contact me or look onto our website. Yeah, and finally, I want to sum up what I presented. Yeah, so first, research software, that software created during the research process and for research purposes. It has specifics like this typical non-functional requirements, the specific setup that people often have limited time contracts, that the requirements are unknown upfront and so on, that have to be taken into account, yeah, and that frame them specifically. Then there are interactions in both directions, so both worlds can benefit from each other, like metamorphic testing or domain-specific languages are very valuable for the research context, but also research citation of software is a benefit in the other direction. And finally, in particular, this intersection is very promising when we look into software engineering and computational science, which is exactly on this intersection. And second, also empirical questions and using research software as empirical context is quite promising. Yeah, with this, I want to refer to the references I cited and used along the way, and close my talk by thanking you all for your attention.